So you got to buy some cupcakes and you see that there's a place that has them on sale for about 80 cents and you're like, "All right, that's not bad, but I would like to get a better deal because you're a poor university student." And so you head over to Costco and they're like, "All right, here's the deal. If you buy cupcakes in bulk, we're going to reduce the price. The more you buy, the cheaper each of them are going to be." And you're like, "Wow, that's great because look at that price effectiveness curve." And then you look at it again and then you realize, wait, the limit as cupcakes go to infinity of money over cupcakes goes to zero. You know what that means? If I buy infinite cupcakes, that means none of them are actually going to cost me anything. So, I just gonna buy infinite cupcakes and then I'll have cupcakes forever and that'll be great and I'll be happy and everything. And they're like, no, just that's too good to be true. That's unrealistic. So if you buy too many cupcakes, we'll have to hire some more bakers. We're gonna have people coming in to work on overtime and stuff, and we have to pay them more. So you're gonna have to pay a lot extra if you buy, say, more than like 900 or whatever at a time. And you're like, no, that's terrible because it screws up with that perfect graph thing. And how do you even how do I figure out how to get the cheaper cupcakes? Like where do I stop? Do I stop buying at like 769 cupcakes or 780 cupcakes or 964? Like I have to know. I don't even know how much each of those cupcakes are going to cost me. Like you have to tell me which cupcake is going to be the cheapest. And they're like, "Dude, just chill. Like you're freaking everyone out, like just get out of the store. Like take these cupcakes and leave." And you're like, "Yes. All right. Math." So that situation back there actually had a lot to do with what derivatives are, and let's start by trying to relate the cupcake situation to the idea of derivatives. And I've taken the liberty of building this nice little derivatives calculator thing. As you can see, the variables are already set in dollars and cupcakes, where dollars are the dependent variable and cupcakes are independent. So we'll start with the simple model, where each cupcake costs a flat 80 cents, just like in the beginning of that intro part. And of course, we know that the function is going to be simply the number of cupcakes you buy times $0.8. So what's the derivative? Well, you may have noticed this differentiate button, and when you press it, you get 0.8. And in this case, that's fine because the derivative of a linear function is simply the slope. And in this case, the slope reflects the price of a single cupcake. So how do you get the derivative? Well, for linear functions, it's quite simple. The slope is just given by rise over run. You'll remember this from high school. And in this function, this is given by the delta dollars over delta cupcakes. So change in dollars over change in cupcakes, which makes sense because the price is simply the cost divided by the number of cupcakes that you bought. Now let's move on to a more complex system. Let's model the second situation at Costco, where buying in bulk makes each individual cupcake a bit cheaper. So we're going to graph that, and it's going to look a bit like a curve that sort of slows down as it increases. And the function is no longer linear. So how are we going to differentiate it? Well, differentiation should give us the slope or the price of a single cupcake. And when we press differentiate, we get this odd kind of mess, and it's no longer a constant. In fact, this is exactly what we want because this tells us that the value of, or the cost of each cupcake actually depends on how many cupcakes you're buying. So how exactly do we arrive at this magic derivative thing that tells us everything about the function? Well, let's attempt the rise over run strategy. It might be suited for lines, but we can try to apply it for curves as well. So remember that slope is just the difference in the dollars over the difference in cupcakes. And let's look at the price of a cupcake after exactly 2 cupcakes are bought. Okay, so we're going to put one of our points over there at a 2, and we'll place another marker somewhere else. Let's say at like near 0 or something. Okay, so the slope, we can calculate the slope as, let's see, so let's say the first point is 2, and let's say the other point is 2 plus h. Well, the slope is going to be the function at 2 plus h minus the function at 2, and then 2 plus h minus 2 will be the denominator. So that's delta y over delta x for you. Okay, let's keep going here. Now, we're going to move the second point a little bit closer, and as you move them closer, you can see that the line down there begins to better approximate the function, the line between the 2 points. And so what if we keep moving the points closer and closer until they basically get to the same place? Well, if you use the function, we can see that, it's actually undefined if you put the 2 points at the same, at the exact same place, because the difference will just be 0 over 0, and, we can't have that, because math error and whatever. So how exactly do we get that perfect slope value? Well, we cheat with limits. Limits doesn't care about undefined values. It is the honey badger of mathematics. So let's look at the limit of the slope as distance h goes to 0. So we're going to evaluate the limit as h goes to 0 of that function there. We're going to cancel the 2's on the bottom immediately, and we end up with all these radicals on top, which we don't want. So we're going to cancel. We have a difference of radicals. We're going to multiply both top and bottom by their sum, and we should end up with a difference of their squares, which is going to be 2 plus h minus 2 on top. And then, of course, we can cancel the 2's on top, and we cancel the h, is very convenient, and then we are only left with that h inside, which we set to 0 because that's how we evaluate the limit. Okay, and that simply gives us 1 over 2 root 2, and that's going to be the price of a cupcake at 2 cupcakes. And you might say, that doesn't really look like what we got in the derivative calculator. Well, let's look back there. I'm going to take that and let's sub in 2 for cupcakes. Well, we're going to get the same value, and it's going to tell us the price at exactly 2 cupcakes. It tells us the slope at that exact point. So we can also, do the same thing and solve for the more general form of the derivative. We simply don't have to put in a specific point. Let's just call the variable cupcakes. Right? And we're going to repeat that same, rise over run calculation. There's going to be a lot of copy pasting here, all right? So we just literally replace every instance of 2 with cupcakes. And that's how you get a very simple derivative from first principles. So that's actually the definition of a derivative. It is simply the limit as h approaches 0 of the slope between 2 points, x and x plus h. And we express derivatives with the symbol d of the function over d at x, which, it's kind of reflective of the fact that it stems from the ratio between the change in y and the change in x. So the difference of the output values over the difference of the input values. And of course, the derivative can tell us all sorts of important things about the relationship between the output and the input. In our case, it tells us the price. And we're going to, just talk about one last point quite quickly. Recall in the video that it said that, okay, so the limit as cupcake goes to infinity of d dollars over d cupcakes, it goes to 0. Yeah, this is true because if you look at that derivative that we had there, which is d dollars over d cupcakes, it's actually 1 over 2 root cupcakes, and cupcakes is found in the denominator. So cupcakes going to infinity would actually cause the limit to go to 0. And because the derivative, the price, approaches 0 as you buy infinite cupcakes, cupcakes would totally be free if we could sustain this type of system for infinite cupcakes. Now, this isn't very possible in real life, but you know what? You can believe whatever you want in mathematics, so it's all the more reason to do some math. Cheers, guys!